Welcome to the session on variable acceleration, functions of time, differentiation, and maxima and minima. The objectives for this session are to understand that displacement, velocity, and acceleration may be given as functions of time, and use differentiation to solve kinematic problems. Velocity is the rate of change of displacement. The gradient on a displacement time graph represents velocity, and its formula, or rather the formula for the average velocity, is displacement from the starting point divided by the time taken. The average speed formula is the total distance travelled divided by the time taken. Acceleration is the rate of change of velocity. In a velocity time graph, the gradient represents the acceleration. So acceleration equals the change in velocity divided by the change in time. Let's now take a look at an example of constant acceleration. As shown here in this graph, we have time on the x-axis and velocity on the y-axis. If the change in y is 5 meters per second, this of course represents a change in velocity of 5 meters per second. The change in x, for example, in this example, is 15 seconds. So the change in time is 15 seconds. Therefore, we have that acceleration, which is change in velocity over change in time, is equal to 5 meters per second, which is the change in velocity, over 15 seconds, which is the change in time. And this, of course, is 1/3 meters per second squared. When the acceleration of a moving object is variable, it changes with time, so it can be expressed as a function of time. Similarly, velocity and displacement can be represented as functions of time also. Let's now take a look at an example. The motion of a particle in a straight line is represented by the velocity time graph below. Acceleration is the gradient of the velocity time graph. So we can see the acceleration here, and then here, and then here, and then here. And this has been represented, of course, by the gradient. The gradient of the curve is increasing. This represents increasing acceleration. In this graph, let's see what happens to the gradient. Here's one, here's another, and another, and another. The gradient of the curve is decreasing. This represents decreasing acceleration. Suppose displacement s of t is a function of time. The velocity v of t is ds dt, since velocity is the change in displacement over change in time. The acceleration a of t is dv dt equals d2s dt squared, since acceleration is the change in velocity over change in time. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's look at example 3a first. A particle moves in a straight line so that its displacement, s meters, at time t seconds from a point 0 is s equals t cubed minus 4.5t squared plus 6t for t greater than or equal to 0. Find s when t equals 2. So let's solve this. We have the formula for s, or the equation for s. So when t equals 2, we simply plug that in to the equation, as shown, to give s equals 2. So when t equals 2, s equals 2 seconds. Now let's have a go at part B. Find the values of t when the particle is at rest. So let's solve this. Of course, we have the equation for s as shown. We also know that velocity, or v of t, is ds dt, which means we need to differentiate the equation for s in order to find the equation for v. So let's do that. We have t cubed being differentiated to become 3t squared. 4.5t squared becomes 9t, and 6t becomes 6. At rest, which is what we're required to find, we have that v equals 0. This implies that 3t squared minus 9t plus 6 equals 0, as shown here. And so we're solving this quadratic. We've clearly divided through by 3 in order to simplify this, as shown. And so if we factorize, we obtain t minus 1 times t minus 2 equals 0. And therefore, t equals 1 second or t equals 2 seconds when the particle is at rest. And now for part C. We are required to find the initial velocity and sketch the velocity time graph. So let's solve this. So here's our equation for s and our equation for v as calculated in the last part of the question. When t equals 0, we also have that v equals 6. So the initial velocity is 6 meters per second. If we factorize the equation for velocity, we obtain v equals 3t minus 3 times t minus 2. This implies that the curve cuts the x-axis at t equals 1 and t equals 2. And so here's our curve. Here are the intersection points of the x-axis and the intersection point of the y-axis. Now let's have a go at part D. We are required to find the time at the minimum speed. So let's solve this. The minimum speed occurs at the turning point or when the gradient of the velocity time graph is 0. And this occurs here, as shown in the graph. Our equation for v is 3t squared minus 9t plus 6. Therefore, acceleration is 6t minus 9. We simply need to differentiate the equation of velocity to obtain the equation for the acceleration. So 3t squared becomes 6t, 9t becomes 9, and the constant becomes 0. So a equals 0 implies 6t minus 9 equals 0. And so t equals 1.5 second when a equals 0. And now for part E. Find the acceleration when t equals 3. So let's solve this. We have the equation for velocity, and we also have the equation for acceleration. When t equals 3, we simply plug in t equal to 3 in the equation for acceleration, as shown, to obtain a equals 9. So when t equals 3, a equals 9 meters per second squared. And now for part F. We are required to find t when the velocity is 36 meters per second. So let's solve this. We have the equation for v as shown. So when the velocity is 36 meters per second, we have that v equals 3t squared minus 9t plus 6 equals 36. Rearranging implies 3t squared minus 9t minus 30 equals 0. And factorising gives us t minus 5 times t plus 2 equals 0. Hence, t equals 5 or t equals minus 2. But t is greater than or equal to 0, and therefore v equals 36 meters per second when t equals 5 seconds. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve part A first. A particle is moving in a straight line. Its displacement, s meters, from a point 0 at time t seconds is given by s equals t cubed minus 4t squared plus 4t for t greater than or equal to 0. Find s when t equals 3. So let's solve this. So we have the equation for s, and when t equals 3, we simply plug that in to the equation for s, as shown, to give s equals 3. So when t equals 3, s equals 3 meters. And now for part B. We are required to find the time taken for the particle to return to 0. So let's solve this. So here's our equation for s. This is the displacement from point 0. Find the times when s equals 0 and subtract to find the time taken. So s equals 0 implies t cubed minus 4t squared plus 4t equals 0. So if we factorise this to obtain t times t minus 2 all squared, we have that s equals 0 when t equals 0 or t equals 2. The time taken is therefore 2 minus 0, which equals 2 seconds. And now for part C. We are required to find the initial velocity and sketch the velocity time graph. So let's solve this. Again, we have our equation for s, and differentiating gives us the equation for v, or velocity. When t equals 0, we have that v equals 4. We've simply plugged in t equals 0 into the equation for v to find v equals 4. So here's our sketch. The initial velocity is 4 meters per second, as shown here. Now let's find the values of t when the particle is at rest. Again, we have our equation for s and equation for v. At rest, v equals 0, and therefore 3t squared minus 8t plus 4 equals 0, and this implies t equals 8 plus or minus 4 all over 6. We've simply solved the quadratic. This equals 2, or 2/3, as shown in the graph. For part E, we are required to find the maximum and minimum speed in the interval t between 0 and 2. So let's solve this. Here's our equation for s and our equation for v, and now also our equation for a. We've simply differentiated v. The minimum value of v occurs at a equals 0. Therefore, at the point t equals 4 over 3. This implies that v equals minus 4 over 3. Here we've simply plugged in the value of t equal to 4 over 3 into the equation for v. So here's our minimum turning point. The maximum value of v occurs at t equals 0. And t equals 0 implies that v equals 4 from our equation. This brings us to the end of this session. If you have understood its contents, you should be able to understand that displacement, velocity and acceleration may be given as functions of time, and use differentiation to solve kinematic problems. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.